Thank you, Jack. Good afternoon, everybody. Thank you all for coming. I'm Wayne Drooks. I'm the Mechanical Department Manager in Integrated Design Group in Boston. So power utilization effectiveness, or PUE, has become the most identifiable metric for data center infrastructure system efficiency and energy savings today, as you just heard. I'd like to share with you today some PUE modeling studies that we've been running at Integrated Design Group, and I'll briefly describe our calculation methodology. We'll run through an example that compares PUE for different systems, locations, and operating conditions, and we'll identify some potential cost savings associated with improved PUE and the most important factors affecting data center PUE. It's well known that cooling systems utilizing some sort of economizers are most efficient, and we can show that IT space operating conditions allowing larger temperature and humidity ranges increase economizer operating hours. This results in significant PUE improvements and operating cost savings. I'm sure that most of you are familiar with PUE, but I'd like to quickly define what it is. So according to PUE is the metric everybody knows, developed by the Green Grid for measuring data center infrastructure system efficiencies. It's the ratio of total power, which is the energy in, over the IT equipment power that's developed, or basically your work out. In other words, it's the efficiency of infrastructure systems, which consists primarily of cooling and power distribution. The lower the PUE, the better it is, with 1 being the lowest possible ratio that you can get. That's equivalent to 100%. Data center efficiency, or DCE, is basically the inverse, basically the inverse of PUE. There it is. And that's sometimes used because 1 or 100% would be the highest number used there. And it's important to remember that PUE reflects energy use only. Capital costs, power rates, and water rates are not considered in there. So it's only one piece of the puzzle. Decision makers have to understand that and consider multiple factors. What are typical PUE values for existing data centers? We just saw 1.04, so that's pretty good. Since you can't get better than 1. We're going to generate power. So here are some documented PUE studies representing averages of many types of data centers in many locations. Unfortunately, some of the reporting requirements of some of these studies really weren't very well defined. It's hard to tell where the measurements were taken in the building and whether these are annualized or instantaneous or whatever time period was used to calculate these PUEs. But the trend here, you can see the trend from 2006 to 2011 gets better. There are more data centers surveyed, therefore there are more data centers that are capable of measuring this. And so you can see that the trend gets better, showing that the importance of PUE. The best PUEs are the ones you just saw, 1.04, typically 1.3 down to 1.04, is typically gotten by companies that are willing to greatly expand their IT space conditions. So, you just heard eBay will allow up to 95 degrees in some of their spaces. The higher you can allow, the more you can expand that temperature range and humidity level, the lower you can get your PUE. That gives you the more hours that you can run on economizer cycles and not use mechanical cooling. So a straight calculation for, what kind of savings you can get by improving your PUE. Basically, a straight calculation for a 1 megawatt facility at 11.5 cents per kilowatt hour could be as much as $100,000 in annual energy savings. That's pretty good. But you have to remember that that would be improvement of a specific data center and not something that you could compare, well, if this data center in Phoenix is 0.1 better than this data center in DC, then I'm going to save $100,000 a year. That doesn't work that way because your power costs may be different and everything else may be different, your capital costs and all that as well. The key factors for monitoring PUE are system, location, and operating conditions. We like to use a simple driving analogy for these factors. You can think of the system as what type of car you drive, what kind of mileage you're getting. You can think of your location as where you drive, is it city or highway, and you can think of the space conditions as how you drive. She's probably driving an old Eldorado, 78. Yes, she drives like my mother-in-law. So each of these factors contribute to overall performance, and any one could be dominant under the right conditions. The results I'm going to show you in the following slides indicate that IT space operating conditions seem to have the highest impact on PUE. So it's how you drive. So let's look at an example. Give up. All right, so we can look at 3 regions. We picked Dallas, Boston, and San Francisco because the climates are so different. We're looking at 4 infrastructure systems here. Air-cooled chillers with CRAH units, DXRTUs with air-side economizer, water-cooled chillers with CRAHs, and then water-cooled chillers with CRAHs and water-side economizer. Space operating conditions, we took 2. We took what we're calling a conventional condition, and we took what we're calling an ASHRAE hybrid, which allows you to go to the ASHRAE recommended temperatures and their allowable humidity ranges. So if you look at these operating conditions, which appear to be the most important input here, operating condition A, which is the conventional ones, we're taking the temperature controls at the return air of the CRAH units at 78 degrees. The humidity range is 35 to 55%, which is very tight, and the chilled water temperature is maintained at 45 degrees all the time. And that's a function of the fact that the humidity, the relative humidity in the space has to be controlled so tightly. If we go to the ASHRAE hybrid condition that we were looking at, this is the recommended, we use the recommended ASHRAE temperature range, which is 69 to 80.6. We control the temperature in the cold aisle, which makes a lot of sense. That's the inlet to the servers. Delta T on the servers is typically 25 degrees. Humidity range, this is the big one. We've gone to allowable rather than the recommended, which is their widest range. That's 20 to 80% relative, and with a maximum dew point of 62.6. And also, we've allowed the chilled water temperature to be reset up to as high as 60 degrees, if it's possible. So when you don't have to dehumidify, you only need to maintain 80%. then you can raise your chilled water temperature, which makes your chillers more efficient. This is the first. This is the input sheet of Train Trace, which is the software program that we use to calculate the energy loads, the cooling loads and the energy loads for any building. It calculates on an hourly basis throughout a typical year. And just to show you, this is the typical input. You can see that we've got, this one here was what we used for San Francisco. This is what we use for San Francisco. And the inputs are all in here. We have 3 different alternatives in here, different systems that we used. This is just an example. That's the first step we do. The final step we do to calculate PUE is we input the data that we get out of that Train Trace run into our own spreadsheet. And here we take the information that comes from Trace is up here, typically the mechanical loads, and it spits out on a monthly basis and an annual basis. We then add in electrical distribution system losses, UPS, switchgear, all that, and distribution losses, total it all together on a monthly basis and average it out for the year. This is one calculation that for one set of combinations. So if you were looking at our example, which had three regions, 4 systems, and 2 operating conditions. So you're looking at 8 by 3, 24. This would be 24 times that we had to recalculate this to get each of these numbers here. So these would be the results of our example. If you look at space condition A, which is the conventional conditions, and you compare Boston, Dallas, and San Francisco, you'd expect that San Francisco would have the best PUEs, which it appears to have. They're all the 1.2s. And that's because you'd expect that they'd be on some sort of economizer, probably air, definitely air, nearly all year round. The interesting thing here is that the one best PUE for this condition happened to be Boston with a waterside economizer. And that's just because of the cold weather in Boston. It allows you to be on waterside economizer longer than San Francisco would allow you to be on airside economizer. Now also, if you look in general at the numbers here, and you look at space condition B, which was that ASHRAE hybrid, which expanded those temperatures and humidities a lot, you can see that in general, all the numbers come down for each region and system combination. And then what really comes down a lot is the RTU airside economizer here, because we've allowed, by expanding those conditions, here's our 2 conditions that we were talking about. By expanding those conditions, we came down looking in Dallas, down to 1.4, in Boston to 1.37, and in San Francisco all the way down to 1.34. The other thing here is that San Francisco has the best PUE here using an RTU under condition B, but if you went back to condition A, you would have seen that the best condition for San Francisco was actually a water-cooled chiller with CRA. So it was a totally different system for the same region. So what this is showing us is that there is not one system or region that is best. You have to look at every one. So if we take a deeper look at the reasons for these results, here's where I'm going to really bore you. This is the psychrometric chart, which graphically shows all possible air conditions, indicating the relationships between temperature, moisture content, and and density. Simply speaking, this shows temperature ranging from coldest on the left side along the horizontal axis to warmest on the right side, and moisture content from least, from 0 to 100%, going up on the vertical axis. Relative humidity are these curved lines, which run like this. Relative being the key word here. The absolute humidity is the dew point, which runs across horizontally here, which dew point goes from 0 down here up to, I can't read that, but it's 90, I think. So what we have here is, this is the psych chart, which is the same for everywhere. These are the conditions for Boston shown in these colored boxes here. These colored boxes indicate how many hours per year at each of these conditions. So this is, this is a temperature and a humidity level that they occur at. So the red boxes are the most hours, and the blue boxes are the least hours. So if you look at Boston, you see the most hours are down here, which is in these red boxes here are in the 30s, and the relative humidity ranges from roughly down here. I think this is the 30% right here, and up to 100%. So you can see that that's what you'd expect for Boston. So if we look at we create a window in here which shows how many hours per year, which shows what conditions you can run air side economizer on in Boston under condition A, which was our conventional condition. We see here that this box, the hours within this box, total 880 hours of air side economizer. If we go to the ASHRAE hybrid condition and open up those conditions, allowable conditions in the space, the window gets this big. The window goes all the way, like here, this purple line here. So now all the hours within that window are available to run on economizer in Boston. And those hours total up to 5216 a year. Total year is 8760. So that's more than half the year, well more than half the year, that in Boston we could be running on economizer. We do the same thing for Dallas. Now Dallas, here's our weather conditions in Dallas, and here's where most of the hours are. Boston was down here, which was 30 degrees, and a dew point of around 30, which is very low. Dallas, the average, most of the hours of the year are in the 70s here, and the humidity is way up here. These relative humidity lines, 190. This is 100, saturated, 90, 80, 70. So it's pretty hot and humid in Dallas. If we go to... Yes. Well, wait till you see San Francisco. So if we go back to condition A for this and window in how many hours were available for air side economizer and total them up, it's only 1,645 hours a year. These numbers go back to the PUEs. If you look at the PUEs that we had, sorry, too fast. So if you look at the PUEs that we had, Dallas actually had fewer hours than Boston on air side economizer. So their PUE under condition A was 1.68 versus Boston, which was 1.67. So Boston was actually better, had more hours. If you go back to Dallas here, so that was condition A. Now if we go to condition B, where we've opened up the allowable space conditions, now our window's here again, and we have all these hours available, which bumps us up to 4617 hours. So more than half the year also in Dallas, you could be on that. Now we go to where nobody wants to live, San Francisco. So here you can see, here's where the conditions are in San Francisco. So this is 50 degrees right here, and everything to the right is warmer. This is, you can see it better on here. That's like 60 degrees right here is 60 degrees. So most of your hours are between 50 and 60. The absolute humidity, the dew points are between 40 and 60, which are pretty good. If you look at condition A, the window for condition A, you've got this many hours that are available for economizer, 5,200 hours. And then if you go to condition B here, you open up those conditions in the space, and look at this. Here's your window, and almost all the hours of the entire year except for 16 are within that window. Now this is a combination of full airside economizer and partial airside economizer. So there are times here when you could be running your mechanical cooling equipment because you just can't make enough, get the air to the conditions that you need. But that's pretty amazing. So this is why when you looked at the PUE for San Francisco and condition B, you look at the condition B, the RTU came all the way down to 1.34, which is the best number that we've seen out of any of these combinations at all. And their RTU airside economizer for condition A was 1.45. So it made a significant difference, as you could see graphically on the psych chart. But like I said before, the best under condition A, the best for San Francisco was using water-cooled chiller. So then we took a look at, we've done thousands of these combinations. Most of them thanks to our friends at Digital Realty, who every day come up with, what if we try this? So this, yeah. This is one of our spreadsheets. I know you can't read it, but I wanted to show all the different results that we got and what was going on here. Along this column here are 9 regions that we looked at. These white columns here are 8 systems that we compared. And then we compared 4 space operating conditions. The ones that I've been talking about in our example, A and B, this is A, the conventional. And then each of these space conditions, we opened up the temperature and humidity ranges to something that we were considering would be reasonable. And then we went all the way to what we have as our hybrid, which is the most wide open that we would think. And what we did is we formatted all these results. Each of these results in color, red to green, are PUE results. And we formatted them with the best ones being green, the lowest PUEs, and the highest PUEs are red. And when we looked at this, we said, look at that. A far greater number of greens are on this side of this table, and it actually increases as you go. So this is showing us that the space operating condition has more impact than the system you choose or the region you're in for PUE. So in conclusion, improved PUE relates to reduced energy usage and cost savings. There's no single best system or location, and the IT space operating conditions have the biggest impact on PUE. And that's because our expanded space temperature and humidity range relates to more economizer hours, which relates to lower energy use, which in the end relates to lower cost. However, you still have to remember that PUE is only one piece of the puzzle. It only reflects energy usage. Capital cost, power, and water rates are not included. Therefore, return on investment and total cost of ownership must be considered whenever you're looking at these. That's it. Have any questions?